sure everybody, there seemed to be the normal confusion between the points in the ambient space, 2D or 3D, for example, and the points that the PDMs live on, a whole PDM lives on. So let me make that clear. Here, up here, is an example of 8 points in 2 space. 1, 2, 3, 4, 8. Yeah. Anyway, lost it here. 1, 2, 3, 4, 5, 6, 7, 8. That's a PDM. It's a collection of points that's data for one instance of an object. It may be a collection of points on the object, right? 8 points. After that 8-point tuple is aligned, you get something on a single point on the sphere, which is the shape space. This is the points in the data. This is the points on the shape space. The shape space here is a sphere. And it's a sphere of dimension 2, which is the number of dimensions of the board, times 8, the number of points in the PDM, minus 4 because you need 2 degrees of freedom for translation in 2D, 1 for scaling, and 1 for rotation. Rotation in 2 space is simply an angle. So that's why the 4. So this thing is in a sphere. The shape space is in a sphere of dimension 12, 16 minus 4. And this whole PDM is a single point on that shape space. Okay? And if I have another PDM, which is another example of a representation of an object, it'll be a different 8 points. And it'll also live on the same sphere. So this point is there, but another point in another place is maybe here. And if you have 4 PDMs in your sample set, you will have 4 points on the shape space. Important to distinguish the ambient space here, where the data is measured, and the shape space over here, where each PDM here lives on a shape, is a single point in the shape space. Yes?
Okay, so the top 2, those are both the same space.
They are the same sphere. I've just shown you 1 point from this PDM. But now, if there are other PDMs, you'll
Okay.
have mappings on to so on from them. Okay, but if these points were in 3 space, so maybe this point was out here somewhere and this other point's back there, but still 8 points, right? They happen to be in the boundary of my hand or something, and the points are the fingertips and the crotch points and so on. Then you'd have 8 points in 3 space, which would live in a sphere 3 times 8 minus 7. Why 7? Because it takes 3 translations, x, y, z, to center, 1 to scale, and 3 to rotate. Okay? And so it's a sphere, and now a sphere which is 17-dimensional. And this whole PDM with 3D is, again, a single point on the shape space. And then if you had multiple examples of these, say 4 of them, then you'd have 4 points on that very shape space. Is there any confusion about that? Okay, so now I'm ready to take general questions. What questions does anybody have from the material we talked about last time, or any time? I guess none, so let us continue. So, for a single sphere, for data that's on a 2-sphere, so a single direction is your exemplar. Now it's not points, it's a direction. And so, as I said last time, we take each one of our hands. Let's take the normal at some knuckle here in my hand. The normal there is a sample, and that sample lives on a two-sphere. And one for each of you would also live on a two-sphere. So it'd be a mapping not of a PDM to a sphere, to a shape space, but now the shape space is a two-sphere, and each one of our normals is a data exemplar that maps onto that two-sphere. But here, I've talked about data that maps on spheres of dimension higher than 2. And so we have this example of an SM, S to the M, which is to say an M-dimensional sphere. Here M equals 2 times 8 minus 4, whatever it is, 12 here and 17 here. Okay. Whatever the dimension of the sphere is, we say we're going to do PNS. We're going to take the data on that sphere and successively lower that dimension to successively lower dimensional spheres, each time projecting and getting out one feature. And so to take a sphere of dimension 12, for example, if you have enough data, so there's more than 12 or 13 cases, you'll be starting out with a sphere of dimension 12. You'll lower it to dimension 11, and that will yield one feature per point here. Right? Each one of these points here will get one derived feature from going from a 12-dimensional sphere to an 11th. And then we project that data onto an 11 sphere. And then we play the same game on the 11th sphere. We derive one derived feature, which is the distance of the distance of the point to the derived sphere. That's shown here, where the derived sphere here is this. This is a two-sphere. The derived sphere would be a one-sphere, and we're talking about distances of the point to the one sphere. Geodesic distances are those derived features. Go ahead.
So the 11th sphere is a subset of the 12th sphere?
Yes, it is.
Okay, so then it's geodesics along the 12th sphere.
And then, yeah, so that's what, yeah, exactly. Just as shown here, the subsphere is on the higher dimensional sphere, and the distances are distances between the point in the higher dimensional sphere and the typically small sphere that is the 11-dimensional sphere. Clear how that goes? And then we repeat that, and the result is for an M sphere, we end up with M features for each point. For each place, when I say each point, I don't mean each of the basic points, I mean each of these places on the shape space.
So that's the number of PDMs.
What?
That's the number of PDMs.
What's the number of PDMs?
The number of...
The number of PDMs here is 4, in which case you...
Oh, okay. Okay.
In which case you, for each of the 4, you would end up with 12 features.
Okay. Even though, okay, we talked about what happens if it's overdefined. Or, no,
Say louder.
I guess we also talked about if basically there are spheres that exactly fit those points. So you can...
I don't know what you mean by exactly fit the points. The points have been mapped. Each place, each PDM has been mapped onto a single point on the shape space. I don't know what you mean by...
With the nested spheres, like any sphere of dimension 3 or larger will exactly fit those points. Or there exists a sphere
Yeah, there exists a sphere.
for your larger bed.
Let's be careful. If you have capital N data points, there is a sphere of dimension capital N minus 1 that fits that. And so in my particular example with only 4, I can start with a 3 sphere because I know all the data. I don't have to go from 12.
Because they're 0.
What?
Because they're 0.
What's 0?
I mean, I guess the geodesic distance, so there's a 3 sphere that exactly fits
There's a 3 sphere that exactly
4 points.
fits
4 points, so the geodesic distance from
all 4 points. That's
onto
right.
that sphere is 0.
Exactly. And then you would start with a 3 sphere, go down to a 2 sphere, and then a 1 sphere, rather than having to go from a 12 sphere to an 11 sphere to a 10 sphere to a 9 sphere. But if my number of points was 40, I'd still start at 12.
Yeah.
Okay. So the point is, things that live on an M sphere generate M-derived features. And now we can represent any PDM, the ones that we use for training, or anyone else that we're going to use later for classification or whatever, using these M-derived features. I will note that the projection, so the relationship of a sphere to a subsphere can be understood as a pole and a latitude, right? If you look at this diagram in the upper left, the subsphere, which is the dashed circle up above, is a latitude of a sphere whose pole is up there in the, it's called W super 1. Yes? That's the pole of the sphere. For that pole, you could say this guy's at some latitude from that North Pole, right? And so at each one of the stages, the software records the pole and the latitude of the subsphere. And then when you get a later point on the high-dimensional sphere, and you want to find its features, you use the already computed polar system at training to do the derivation of the projections onto these successive subspheres to produce its M features. Questions? Is that clear? Take any point, any new point, like the one that you have up here but wasn't used in training. It's a point in the subsphere for a new PDM. And you just, you know what the subsphere is, you can project it, and that gives you the feature. And then you project that down onto the subsphere that you have here, and you play the same game, and you project it on its subsphere, and you get another feature. And you play that game all the way down, and you end up with, in this case, 12 features for my, if I had not 4 points, but 40 exemplars in my training case. Okay, but the problem is that most of our data that we're going to be dealing with in this course is shape data that isn't just points. It's, for example, normals. And so now instead of one normal on my hand, I'm going to have a normal here, a normal here, a normal here, a normal here. I'm going to have a whole collection of normals. You've seen that. You've seen the normals example before. I don't know. know if I need to bring up the slide that shows them. But the point is that a set of normals is on S2 cross S2 cross S2 cross S2. Yeah.
There's a question on Zoom in the chat.
Okay. Question on Zoom. Go ahead.
Yeah, hi, thanks. So I'm just trying to find some intuition about the features that we learned. So I know for PCA, like the first principal component is where the maximal variance lies, so like where you'd lose the least information if you projected them.
And that's the same here, except you get them in reverse order. So you get the least variance one first.
Okay, do they actually map? Like if I, do I find the same vectors this way? Just in backwards order?
If you had a Euclidean space, you would. But this isn't a Euclidean space. Spheres and polyspheres are not Euclidean spaces. And so I've basically told you that going forward is a bad thing to do. If you went forward, you would get a different answer, and it would be a bad answer. Because the successive representations no longer lie within the data if you go forward. And so you must go backwards. For PCA, going backwards is the same as going forwards from the mathematical point of view. And if you only want a few of the features, so you're only going to need the first five PCA components, then it makes sense to go forward. But here, you can't go forward because it doesn't behave right. You have to go backwards. If you're in a 12-dimensional space and you're only going to want 5 features, fine, you go 12 to 11 to 10 to 9 to 8, 7, 6, 5, 4, 3, 2, 1, right? And then you have 12 features, and then you throw away the first 7 that you got. But you need to do it backwards. Does that answer the question?
Yeah, I think so. Yeah, thank you.
Okay, I also want to point out that these features are all angles. A distance on a sphere, a geodesic distance on a sphere, is in units of radians. Okay, so our problem then is not just M spheres, in particular M equals 2, but polyspheres. And we have polyspheres, as I said, for example, because we have normals or other directional components that we'll see in skeletal representations. Yes?
I don't understand what a polysphere is.
A polysphere is, okay, so here's an S2, an ordinary 2-sphere. Here's another S2. A whole bunch of, here's another S2. You have N S2s. This is for the first normal. This is for the second normal.
Okay.
This is for the third normal in a particular instance. Right? This is one hand, and it's
Okay.
50 normals.
So a tuple of normals is in polysphere S2 to the 50.
And it's due to the n, right.
Okay.
And so a single collection of normals for a whole hand, one data item, is going to be a point that has the first normal and the second normal and what did I say, 40 normals. I said 50, I guess. But anyway, the 50 normals, you're going to have 50 spheres and one point in shape space. It has its value. Sorry. Somebody. See if I don't know how to turn this off. Just. Sorry. Okay, so this is the place of the first normal, this is the place of the second normal, but the tuple is the whole shape space, the Cartesian product of these 52 spheres. So one data item is that whole thing. It's really a 100-dimensional entity, 50 times 2. Right? That's a Cartesian product. Of two spheres. And so somehow we've got to get down, we've got to get 100 minus minus 7, if I'm in free space. We need 93-dimensional thing that we're going to want to go from 93 to 92 to 91 to 90 and so on. So we have to somehow get successively, the idea is to be able to get 93-dimension descriptor of this and then throw away the higher, the ones that are limited variance. There are two ways that people have developed for doing that. The simplest one is, don't bother me with 100 dimensions. Let's lower this guy by itself, just to do ordinary two-sphere analysis, and thus yield two derived features. And on this guy, we'll also generate two derived features. Okay, so I've got 100 derived features. 50 times 2, right? The problem is as follows. In ordinary PCA, in Euclidean space, you're taking into account the covariance between all the features in the space as you're developing this descriptor. Here, you're taking care of the nice covariance over 2 dimensions, but not the covariance of this with this. The features from here are not, we haven't taken care of the way in which things on this sphere vary with things on that sphere, or any of the other spheres. So we end up with perfectly nice 100 derived features, but we haven't yet, but now they're in Euclidean space, pseudo-Euclidean, approximately Euclidean space. This sphere fitting basically makes, for most data, makes the distribution of the points act like you can do sum of square differences on the derived features. And so I have 100-dimensional derived features, and now I have to do PCA to get on that to get the ultimately derived features. So it's a sphere by sphere analysis to each getting the features from it and then taking all those and doing a PCA on the result. Yeah?
I missed where the directions are coming. Like, what are these end directions?
The normals.
To what?
My hand. If I'm doing, boy, sorry, I don't know when I last had a hand picture on here. I should have. Let me find another slide that has it for you.
These are the normals or more.
Okay, I had a picture of a piece of surface, and at every place on the surface, there was a normal. So this is an example of this for this data item, which I say is my shape, my individual hand that I want to do statistics on. So I have a whole bunch of hands, and for each one of them, I have 50 normals. One at each of 50 points.
So the point locations are defined.
Yes.
Okay, because yeah, normals is two-dimensional, but the point.
Okay.
Wait, okay.
Yes. So Sam asked correctly. the point locations are defined. Or you can let the point locations be part of your data. And if the point locations are part of my data, then I have over here a very high dimensional sphere that designates where all the points are.
And we would need to do PNS on that separately.
Yep.
And then then that would mean we're doing PCA over.
Well, everything all together, all these derived features from the respective spheres would yield their appropriate number of features, and then you would do a PCA on that whole set of derived features. Got it?
Yeah.
Payment systems. Every time I get that. Okay. So, now our feature analysis yields maybe if we had 50 normals and 50 points. The 50 points would produce a 3 times 50 minus 7 dimensional sphere here. Which, if I had enough data, would yield a 143 dimensional, 143 derived points. And I'd have 50 of these, which would produce another 100 points, derived points. And then I would append all those points and do a PCA on them. Okay. Some effort has been put into trying to figure a better way to put all these together onto one big supersphere. To project the data, all this data onto one big supersphere of dimension. In this example, what did I have? I had 243, it would be a 243 dimensional sphere. And then play PNS on that the data mapped onto that sphere. I'm not going to get into the details here. The point is that because we know how to lower dimensions on spheres, it was clever to try to map the data onto spheres. But in general, the question of how do you work on a manifold with successively lower dimension manifolds that you map onto via this general approach is a research problem. And the way people are doing it now is this way that I just described as a sphere by sphere followed by PCA. In fact, one of the projects in this course by one of the students taking it for credit, Michael Niesenson, is trying to do this on Sn cross S, S to the n cross S to the n, just two of those spheres, and doing something clever on how to map essentially to a sphere. The trick essentially is to get the distances on their respective spheres to map into corresponding distances on the supersphere. Okay. This whole business then gets even more complex by the idea of Xavier Pinnock that, wait a second, I'm making a decision on going from sphere n to sphere n minus 1, independent of the decision going from sphere n minus 1 to n minus 2. and that trying to make all those decisions at once can produce a better mapping of all the spheres onto the other spheres. And he has work called barycentric analysis, which is theoretically very interesting, but has all sorts of difficulties yet to be researched and is not being routinely used yet. Okay, I'm done with the general point of dealing with spheres and polyspheres. But I want to teach you about the granddaddy of this kind of analysis that you will find in the literature. And it's in work by David Kendall. There's also related work by Frederick Bookstein. It's all described in Dryden and Mardia's 1998 book. Dryden and Mardia also produced a book from 2016, a second edition, and the 1998 book is on reserve at the library, and the 2016 edition in electronic form is also available on reserve, but you don't need to worry about that because you can just search for it online, and the whole book is there for you to look at online. But in any case, Dryden and Mardia, Ian Dryden and Kanti Mardia, are absolutely excellent interpreters of the ideas of these other people, like Kendall and Bookstein. And rather than go to Kendall's papers or Bookstein's papers, I recommend you go to these books if you're interested in PDM analysis. And in particular, I'm going to talk about the Kendall shape space. And here, they take advantage of the fact that in 2D, you can think in terms of complex numbers. It's the same, by the way, it's going to be the same representation, but a different way of obtaining it. And so I'm going to talk about that. In complex space, where you have a real axis and you have an imaginary axis, a duple z equals x plus iy is a point in complex space. And points in complex space, you can talk about the unit circle in complex space, which is just e to the I theta, where theta is angle around the circle. And you can describe any point in terms of its r and its theta. So x plus iy ends up being r e to the I theta, where r is the square root of the sum of squares of x and y, and theta is related to the tan inverse of y, the y over the x. Right? So now their idea is that let's think of these points, x, y's, these guys over here, as r e to the I thetas. So you're going to have an r and a theta for every point instead of an x and a y. So we can turn that in. Okay? But we, of course, learned that we should remove translation. So these x's and these y's should be after translation. Right? to their center of mass, you know. And we also want to remove scale, which is going to be a collapsing of these points in this space. Okay, so this PDM over here will have been centered, and they will have been re-represented, it's supposed to be a circle, re-represented in terms of their R's and their thetas. And they point out that that rotation, that scaling, is simply multiplication of any point in the space by an S naught, that's scaling factor, and rotation is just multiplication by e to the I phi by, where phi is the rotation angle into space. And so they say, okay, take that number over all possible scalings and all possible rotations, all possible S zeros and all possible phis, and consider the space of z's, r e to the I theta, by w's, which are alpha. I called it alpha here, so I should call it here too. Alpha e to the I phi, where alpha is the scale factor, and this. And so they say there is a equivalence class of all z's multiplied by all possible alpha e to the I phis. And then this space, which is called the complex projective space, Cp to the k minus 2 for k points, is their representation of PDMs. I mean, it is the shape space onto which this thing maps. Well, heck, there's nothing new here. It's just that you happen to have thought of it a new way. And you're going to do your statistics on that, but look, it's just living on spheres as before. There's nothing essentially different. Yeah, go ahead.
Oh, no, it's me.
You okay?
Well, I mean, actually, okay, so Cp k minus 2 it's all possible W's times all possible
The equivalence, well,
equivalence class.
it's the equivalence classes over W's.
Isn't that isomorphic to just C, though?
It's like isomorphic to what?
To complex numbers?
It's isomorphic to the shape space the spherical shape space that we already talked about for PDMs.
Oh, I see.
This is my question. So, CPK minus 2, shouldn't it be CPK minus 1? Because really, when you take that equivalence class, the alpha and phi only constitute a single complex number.
Yeah, but it's two. Yeah, but it's two.
Then why don't you call it CP2K minus 2?
I don't know.
Okay, never mind.
Okay. I understand this is what they've done. But I haven't gone into it enough myself because I don't consider, these days you should do what I've been telling you now, rather than, I'm just trying to say there is an equivalence for this thing. So you end up with distances on unit spheres just as before, and you can do statistics. But there's an interesting further analysis of this, especially for the situation where you have 3 points. Your number of points here is not 8, but 3. Okay, so we're going to have 3 points here. And those 3 points can be understood to form a triangle. Right? 3 points in two space, what's the dimension of the space going to be? It's going to be 2 times 3 minus 4. 2. Right? A triangle in two, representing 3 points in two space, after alignment, lives on a two sphere. And what about for 3 dimensions? Well, it's 3 times 3 minus 7. It's a two space. So for both two space and 3 space, the shape space is a two-dimensional sphere, S2. And thus the space of all such triangles lives on a sphere. You see the example here, where the North Pole, the way it's shown here, is an equilateral triangle. Notice these are all scaled triangles, so that their centers are in the middle of them, and their rotation is appropriate. They're rotated in their scale. They all have the same sum of squared distances to their center point. And so you have a space of triangles that live on a sphere, and you can now talk about the distance between two triangles in two. Okay, so now if you have one data set which is a triangle, another data set which is a different triangle, another data set, you have a sample of data sets, you have a sample of triangles. And what you're trying to do is to talk about representations that are related to the distance between triangles, but we know the distance between triangles here are arc lengths on unit spheres. And so the basic point is that if you want to do statistics on triangles, you can do it the way we talked about before, or you can do it in terms of these triangles. You'll get the same result. But our objects are like I have here. Here are 3 hippocampi down here at the bottom. Each of them is made up of a tiling, a mesh of triangles. That is one of the most common representations that we have in computer science for shapes, for their boundaries, is we tile them with triangles. Right? And so now I have, 500 triangles on one of these guys. And how you combine you can do the statistics on each triangle separately, and how you combine all those triangles is, lots of people have had lots of different proposals on how to do it. And my proposal is, you just think of those mesh points as points in a PDM, and you do the mapping to a sphere, and you do PNS on that sphere. I'm not going to go through these various choices. That's a course in itself. Any questions on that? Okay, so far so good. We've been talking about PDMs and possibly PDMs with associated normals, and how to do statistics on that. But an interesting idea comes from, in 3D, comes from the fact that you can take any object like this guy here and consider it as a mapping, an appropriate mapping. We'll see what I mean by appropriate, from points on this to points on this surface. So for every point on the sphere, there is a corresponding point on the object. And here I have, 16 different hippocampi, the blue ones and the red ones. And for each of them, I have done this transformation getting the points that I have over here as mappings of points that are over here on the sphere. When I do that, I can play a game that is akin to Fourier analysis, but for spheres. Fourier analysis has to do with mappings. Let me erase some. If you have a circle, an ordinary circle, and you have a closed curve, and you say this guy maps to here, and as I get to here, I'll have gotten to here, and as I get to here, I will have gotten to here, and as I get to here, I get to here. And so now for each point on the sphere, I have each point on the circle. So for each theta, I have both its x position and its y position. Okay, I have two functions of theta, and theta is cyclic. And so I can do Fourier analysis of x of theta and y of theta into sinusoids, into basis functions that are better be careful here. Let me make these J's. Okay, things are new. New is frequency. You have sinusoids of different frequencies. The bigger the new, the bigger the frequency. And I have x as written as a linear combination of these orthogonal sinusoids and these y's as a linear combination of the same group. And now my features are just the alphas and the betas. I have alpha 0, alpha 1, alpha 2, alpha 3, beta 0, beta 1, beta 2, beta 3. And now I can do statistics on the alpha beta 2. That's great for
What's R?
what?
What's R?
What's the new?
Where's our?
Oh, the new. And the sum zero now.
That's J, not R.
No, what's it in? No, in the exponent.
I 2 by nu sub J theta.
Okay, what's new sub J?
It's frequency.
Oh, right, yeah. And that's, oh yeah, and that's, yeah.
This is some sinusoids at various multiples of a base frequency.
Right.
Well, I'm going to play the same game in 2D, except my basis functions aren't going to be, okay, so just want to write this as sort of general idea. Alpha j, e, I'm just going to call it psi sub j of theta. Where psi sub j of theta is this thing. Right? So a linear combination of basis functions, and this guy here is some over j, beta j, psi sub j of theta. Good? They play the same game for spheres. Except on spheres, we have a theta and a phi. Latitude and longitude as places on a sphere, just as theta tells you places on a circle. And so we're going to have, and we're going to be, our points are going to be have an x value and a y value and a z value. And all I'm going to do here, I'm going to get rid of this middle because it just confuses things. My basis functions are going to be functions of latitude and longitude. And so, gamma j, psi j, theta phi. And so the result is that for any one of these points, x, y, z's, on a now a three-dimensional thing, it's got that x, y, z as a function of theta and phi is going to be written in terms of the alphas times these basis functions that are called spherical harmonics, the betas for the y's, and the gammas for the j's. And now I'm going to take all the alphas, all the betas, and all the gammas, and I can do statistics on them. Ordinary Euclidean statistics on alpha, beta, gamma. When I have Euclidean statistics, I can do PCA, right? Lower the number of dimensions. Okay, so this is all great. If A, I have well-behaved functions psi j, well, it turns out you want them to be unit orthogonal to each other functions, and just like for the Fourier analysis, the sinusoids do it, these things that are called spherical harmonics do it. You can look up the spherical harmonics in any reference. Right? They have nice formulas. They're polynomials times sinusoid-looking things. Better be careful here. I have a typo here. There we go. What a pain. All right. I still didn't do it. This B is supposed to be underlined. It has one B set for the X's, another B set for the Y's, and another B set for the Z's. Sorry for, I'm not going to go through this. You understand that this B set has a tuple, three of them, one for the X components of the points, one for the Y component of the points, one for the Z components of the points. We organize things so that we have known equally spaced points on the sphere, on the two-sphere. And we're mapping each one of the vertices on those to appropriate points on the object. And then once we have those mappings, we have the X and the Y's and the Z's, which we can turn into the alphas, the betas, and the gammas, which are the underlying B's on the formula up there. The alphas are B, the first component to B for the X's, and likewise for the Y's, the second component. Okay. How do we do that mapping between the object sphere and the places on the object. There are basically two ways people have done it. One is based on a mapping that maintains angles. All the little spherical triangles on the sphere stay as all the angles of the map associated triangles are the same. That turns out to be not as good as an alternative which says keep the areas the same. So all these little spherical triangles on the sphere have the same area, and what I want to do is map them onto the object so that the associated little triangles on in our mesh are going to also have the same area. But you will see literature of people who did it with the conformal mapping, which gives you the angle staying the same. You can't do both. Okay, so before I go on to that slide, let me finish what I saw here, and that is once you have all these points, X, Y, Z points that have been mapped, fitted onto these, from which you have gotten the alpha, beta, gammas, you can also take their mean, right? Their center point for a population. Fine. So this just gives you an idea of what the spherical harmonics are like. The first spherical harmonic is uniform on the sphere. It's a constant. It's the same as the zero frequency cosine. You got a constant. Cosine of 0 is 1. The next group have low frequency in latitude and longitude combinations. Right? So you can rotate with one cycle all the way around latitude or one cycle all the way around longitude, or both. And the next ones have 2 cycles in latitude or longitude.